So, welcome again to another session. We are going to examine a titration question. It also involves some redox reaction, and so we're going to dive right into it. This is Mr. Thomas. Welcome to Buckle Down Tutoring Services. The class is an online class, and if you're interested in joining, you can contact me so that you can be added to the class. What you would have recognized, this is the first question on the paper. This is what they do. This is what CXC says. For every first question, more than likely it's a lab related question. You will more than likely also get a graph sometimes, and it is a question that will use up some amount of time. So if you notice what they indicate in bold right here, they would have said do not spend more than 30 minutes on question one. So if and you should be practicing this to time yourself. So while you proceed and you recognize that, hey, so I'm going over the 30 minutes, what you'd have to do is to probably pause and go to a different question because you want to capitalize on the marks. So they know, the persons who are setting the paper, I tell you, say, don't spend more than 30 minutes on that question, yeah, because you have other questions that you would have needed to cover. So while in the exam you have on your watch, and normally they have a clock on the wall, and you see that 30 minutes pass, you just proceed to our next question, and then you come back to this question if you have the time. Time management is very critical when you're doing an exam. Practice, note the time, and just use it wisely. All right, so it says an experiment was carried out. This is all right. Yeah. An experiment was carried out to determine the percentage of iron. So just bear this in mind. We want to figure out the percentage of iron in an iron salt sample. So a salt, as you know, when we're dealing with acid, base, and salts, a salt is a acid that all the hydrogen has been replaced. So this iron salt would have iron plus whatever anion was in the salt, in the acid rather. So if it was hydrochloric acid, it would have been iron chloride, sulfuric acid, iron sulfate, nitric acid, iron nitrate. So it's basically, we don't know which salt it was, but we know it's an iron salt. It also goes further to say a 0.500 grams sample of iron salt was placed in a conical flask. To it, 25 milliliters. As I said, when we see this is the same as what? Anybody knows? So this is the same as 1 centimeter cube. Don't know why my pen is not responding so quickly. So 1 centimeter cube. So if you see that, don't be frightened and say which unit that. Just basically know you're still working with centimeter cube. Now of dilute sulfuric acid. What's the formula for sulfuric acid?
H2SO4.
Wonderful. And so, as I go along, I normally like bring things and prompt you. So sulfuric acid is a dibasic, tribasic, or a monobasic.
Dibasic,
Why is that dibasic?
because it has two hydrogen ions to lose.
Wonderful. 10 milliliters of phosphoric acid and 8 drops of an indicator were added. The contents of the flask were mixed and titrated against a 0.020 moles dm cube solution. So when we see this, what does this mean? When we have 1000 centimeter cube, it basically contains 0.020 moles. Yeah? And so that would have been of potassium dichromate. Now we learned last week about oxidation and reduction. We learned about the concept of reducing agent and oxidizing agent. So can anyone tell me, potassium dichromate? Anybody knows? Is it a reducing, oxidizing? What is it? Anybody?
Oxidizing agent.
So it's an oxidizing agent. Beautiful. What happens to an oxidizing agent? If I'm an oxidizing agent, what is happening to me?
We're being reduced.
So I'm being reduced. And if I'm being reduced, that means I am gaining electron. Not true?
Yeah.
If I'm being
That's
reduced, it means that I am having a lower oxidation state. My oxidation state is decreasing. So this is how I want you to, break down the question and look into it deeper until the end point was reached. The ionic equation for the reaction is given below. So we're looking at the ionic equation. So this is not the full equation. So we're seeing the acid, we're seeing the iron from the iron salt, we're seeing the hydrogen from the phosphoric acid, we're seeing the dichromate. Yeah? And I want you to remember when we dealt with moles, we said that if we look in front of the compounds and we see a number, that number represents the coefficient. That coefficient in terms of moles really tells you how much moles of the substance you have. So how much mole of dichromate we have?
one.
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 Beautiful. How much moles of iron we have?
6.
How much moles of the acid we have?
14.
How much moles of the iron 3?
6.
All right. Now I want to just bring your attention when you examine this. What's the oxidation state of this iron?
2
Plus
plus.
2.
So we said that we say the charge before. So once we know the ion, so this is a +2. And so what's the oxidation number of this?
Plus 3.
Beautiful. What happened to the oxidation state?
It increased.
Wonderful. So let me ask you this. What is happening to the iron 2 in this reaction? Or whatever iron
It's being
salt.
oxidized.
Beautiful. And there's something else we know. If it is being oxidized, that means this iron 2 is the,
Reducing agent.
it look like I can lock off me and go back on my bed then. Not true. So it is the reducing agent. Now when we check, anybody can quickly work out the oxidation number for the dichromate here. So we said that what is the rule? We know oxygen is always -2 unless it is in a peroxide, and it is not in the peroxide right now, we also know that this is a polyatomic ion. And when you sum the atoms in a compound, you should equal to the charge of the polyatomic ion. So it's not equal to 0 in this case. So we see dichromate right here. So we no longer say x. We would have said 2x plus 7, because a 7 oxygen, each oxygen is minus 2, 1 second, minus 2, and we have it equal to negative 2. Not true?
Yes, sir.
And we come to bumps. We know 2x, 7 times negative, negative. And, I'm having some serious issues with students with this little math, this little algebra expression I create havoc in my classes. So we have to get that part there, people. I'm not a math teacher, but a negative times a positive will give me a negative. So I get negative 14, and I'm just showing you in its entirety. Now, when we have two unlike sign, we keep the negative sign. Normally, person say, me I move over the 14, but we want to say if we want to get the 14 by itself, sorry, if we want to get the x by itself, 2x minus 14, we add 14. And if we add 14 to that side, we also add 14 to this side. And I know this might be boring some people, but you have some persons that just may not understand. So we're working it out. Just give me a second again. I think I hear that sound. Did the person enter? All right. So this will be broken down to 2x equal to, what's the answer over here?
12.
12.
Beautiful. And we want to get x by itself. So we divide by 2. And if we divide by 2 upon one side, we divide by 2 upon the next side. So x is
6.
all right. So we know the chromate is plus 6. When we look over this side, see the iron here? What is the oxidation number?
Plus 3.
Beautiful. So watch me now. Remember we said it earlier, We said that potassium dichromate was a what?
Oxidizing agent.
Oxidizing agent. And so in itself, it is going to be reduced. See there? It is moving from a plus 6 to a plus 3. So it is indeed being reduced. It is what is causing the iron to be oxidized. Yeah? So
Yes, sir.
whatever iron 2 salt is acting as the reducing agent, and the potassium dichromate is an oxidizing agent. Not true? So we have a redox reaction happening here. Now, how much moles of water?
7.
Beautiful. So let's get down into the concept of the titration now. We're seeing, and whenever we get these, we have to examine to highlight. Remember, we read the burette from the top to the bottom. Remember the meniscus. So anybody, let me just double check something. Should get a table. Yeah. So the table is there. So somebody just write down the numbers them for me so that when I move down to the table we can have it. So can you tell me what's the reading on this initial?
Two.
So it look like we'll be two.
Beautiful. What is it for the final?
21? No?
Remember 21 would have been here.
Yeah.
So what one of the things I didn't establish what each of these strokes represent though. Each of these strokes. So let's go back to the first one. If I'm here, then this point would have been what?
One.
1.1?
1.1. So we know that this is a point one. So every stroke is a point one. Not true?
Yeah, man.
All right. So if we come to bams and go right here, so midday halfway. So this there, people them are gonna bash me and say me a talk patois. But for the students who are, let me switch it back. So what would we have here? What would we have here?
At a point five, man.
So 21.5. And we go again, we have 21.6, 21.7, 21.8, 21.9. But if you look at the meniscus, kind of below it, not true? Then I center
Mm-hmm.
between, all right, so we are going to work with 21.
21.8.
No, man. Because remember, we passed 8 already, see 8 you say, no?
Oh, so
8.
it'll be 21.9.
And we say the end of the center, so we are going to give it a 5. Because it's the half. Say almost the writer, 2. Not true?
Yes, sir.
All right, so the next one, initial.
Oh, 1.9.
But again, in a reach there.
1.8?
Yeah, man, 1.85. Because again, it's like it's in the center, not true? So right there, so. Yeah? You know, fully reach the 9 yet. I know maybe because of the screen, I'm not sure how clearly the diagram is. And CXC won't penalize you. You know, if you do, if you say 1.9, they're not going to kill you. You're not going to lose a mark because they take into consideration. If you say 1.5 now, which is way off, then you're in a problem. So this one,
21.75?
why we say 7? Cause
Sir,
it's
wait,
7,
hold
she's
on.
7 here, you know. Cause it's 5 years, it's 6 years, it's 7 years. So go on again.
Oh, it's
21.85.
21.85.
Beautiful. What is now?
1.5.
Definitely. Cause I want to straightforward. The meniscus they're right on it. Right on the point 5. What I want here?
19.5.
All right. So again, if you can do that, you would have been able to have your results and you can work with it. So the next question Well, we just do that. Out of, we would have, but please, what you can do, ensure that you read the questions in their entirety. So like for this, it says list the apparatus that would be necessary to carry out the experiment. And most, if not all, we should be, a little bit familiar with titration. And even if you're, one of the things students sometimes even struggle by telling me, but even the question, see it here? If you not list none, see there? See one of the apparatus where you need here, what do we need?
Burette.
Burette. So what you can even do, sometimes even the question itself may have outline. So see it there again, you need for a drop, so you may need a dropper. Look right there, so. It say you need a conical flask, and you must need a beaker. So we need beaker. What else we would need?
A pipette.
A pipette. Watch here, we would have gotten a sample of grams, so we must need a. Or would I get that sample here? Or would I get the mass?
So we need a scale.
Yeah, balance
And we
scale.
need and we need to move away from that. In Jamaican terms, we call everything scale.
Balance.
Thank you so much. So we need the balance. Did we measure anything outside of using the pipette? We would have need well, it says 10 milliliters of phosphoric acid. What we're going to use to measure that? What would we need to do?
Measuring cylinder.
Beautiful. So again, everything when we mention right here, so I question me come back up. So if you really think, and if you never know, persons would are struggling, but me no know what we use, and teacher never give me this, and we create all excitement, but sometimes the answers are actually in the question. You see everything, let me read again, see if we can pick up on anything else we would need. So, yeah,
What about the little metal thing to take out the iron the
wonderful. So,
salt?
as for the spatula,
Spatula.
yeah, man.
Spatula, yes.
So even that, so see there. So we put ourselves in the lab. What you'd have to do is put yourself in the scenario. Usually they talk about a white tile or some white background for when you're doing the titration, so you can observe the color change. So yeah, if you were making the 0.20 moles per dm cube, you'd definitely need a volumetric flask. Yeah. So I hope, and I always say it to students, when you get on the platform, when you're dealing with the class, I know persons may just tend to be there and just looking. Let me see all of who are write down something. You actually jot it down and I go through, so that when you come off the meet and you want to go back, or later on when you're just looking back at the question, you have something to relate to. I don't want it to just be there just looking at what I'm doing. I want it to be actively involved. Not true. So come with your book, come with your paper. Um, so you're more active and just not be there just looking. So one of the things I was asking for you to do is to give me write down the results. So what was the final one for the first titration? Nobody need an answer.
21.95.
sound like one record with somebody. 21, where you saying board run? That? Or 19, but I don't remember. Initial
No, man,
volume.
a 1919 man, I say.
Initial volume. What was it?
2.
So for the first one was 2.
Yeah, man.
So work this out. Nobody not answer me. Them a watch me. Tell them work it out. Suppose me not get it right. That's the answer.
Yeah,
Yes,
man, that
sir.
look like it.
The second titration.
Final volume 21.85.
Initial.
Initial 1.85.
So how much is?
20.
20 flat.
Just put 2 0 there so just hold that decimal place. The final one.
Initial 19.5.
And I think the other one was 1.5. Not so.
1.5. Yeah, man.
You mixed it up. The final one is 19.5 and the initial is 1.5. Oh right.
So how much is this? 18?
18.
Alright, let me
Yes,
double
sir.
double check this again because I hear the sound. My apologies here, hop cross, but I don't know why it don't allow persons. Once I'm not on it, it doesn't. Mm. All right. So look, you see that? Look at that. Look at this. You see how much marks this? You see that? How much marks that? Just
9.
Fuck 9.
just to complete that table, guys. So even if you're not doing a working out yet, but you're reasoning and you're able to read a scale and read the titration, calculate it correctly, you would have been able to get 9 marks. And you're supposed to in an exam and smile, not true?
Sure.
Want to read these out in its entirety. It says use an asterisk. And you see sometimes we don't like follow instruction, We don't like follow instruction. The question say use one asterisk. We got ticky. We got underline. We got circle. Work with what the people them tell you to do. Use an asterisk, use an asterisk. Why we need to use an asterisk? It says to indicate the titration data that should be used to obtain the average titration volume of potassium dichromate used in the experiment. Now, you see, the thing about it, they say that it should be a zero point 0.1 difference. So a zero point 0.1 difference. So when you look at the titration results, it should be of a zero point 0.1 difference. Now with these, I should ask you, sorry, which would I use? When we look at
Sir,
the, go ahead.
sir, last if you could repeat what you said.
No, I was saying in terms of the titration, and even in I'm in a teacher group, and one of the questions that they asked, a teacher was asking, what if the rough. Can we use the rough in the titration? And the answer is yes. But because initially, if you go back up, the first one was the rough, right? Now, see there, it's even mark in a bracket, rough. The concept is if it is near to it, if we have it in terms of zero point 0.1 difference, yes, we can use the rough. So that is possible. So usually students will say, no, we're not going to use the rough, none at all. It doesn't have to be like that. So if the rough is close to the 0.1, we can. So these are the two. So may I put my asterisk. And then you would have had this kind of too much out of the window. Because when you think about titration, we want to think about something that is precise. Even when you're doing it, you want to, when you reach close to the end point, you basically use a drop of the contents coming from the burette to determine the color change or the end point. You don't want too much, so you want it at the precise reading or volume as best as possible. All right. So again, once we do that, see it there, we get a 1 mark, and we are smile, and we are continue. It says, hence, calculate the average volume of potassium dichromate used in the experiment and record the value to 2 decimal places. So the people them specific, guys, not 3. So when CXC goes this specific, you have to follow. You see, you won't get the mark. How do we work this out? If we're gonna find the average, just like if you get a test, you know, when you get 95 per one and 60 per the other, what's your average, or you work out your average?
Add up everything and then divide.
And then divide. That's still not so clear, sir. Divide, what we divide?
You divide the total by the amount of things you added.
Wonderful. So the amount are great. So total divided by the amount of grades that you got, which is 2. So in this case, we're adding. So the 2 we use. So add this for me. How much is? It's a 5. It's a 9. It's a 9. And it's a 3. And then we do what? Divide that
Yeah, by 2.
by 2. And so we should end up with, how are them there? Normally we have person with
19.9776, rounding off to 8. 19.98.
9.8. Sorry about this. Let me write it properly. It's a 19, and everybody can check just to make 9.8. So says everyone. And we don't want to leave the units. So centimeter cube, because it's a volume, right? Yes.
Yeah, man.
It says using the information from C2, again, let me tell you, C2, which is this. Calculate the average number of moles of potassium dichromate used in the experiment. Watch me now. Let's go back. We go back to this part where we have this. You remember this that I evaluated? When you have 0.020 moles per dm cube, what that is saying is how much is in 1000 centimeter cube. Not true? True?
Yes,
Yeah,
sir.
man.
But the question is now saying to us, since we took out a portion of this potassium dichromate solution, and when we used it, it would have been, sorry, it would have been 19.98. So you know I use conversion, I don't go the cross multiplying. So I know 1000 centimeter cube based on that moles per dm cube is 0.020. That was it.
Yeah, man.
Moles. And I say once I get to this is my conversion factor. I'm going to be creating a fraction from this. So I know I used in my experiment 19.98 centimeter cube. I'm going to be multiplying it. And as I said before, I'm creating a fraction from this. So again, if I take out 19.93 centimeter cubes of this potassium dichromate solution, will it have in less or more moles?
More. Less.
Gonna have less. So just think about this. You mix up a big batch of Tang or Kool-Aid in a jug and you take out a cup. Will the cup have in the same amount of Kool-Aid as what was in the initial large jug?
No, sir.
So it's the same concept. You have this big volumetric flask of 0.02 moles of this potassium dichromate, and you would have extracted some of it. You take out 19.93 centimeter cube. Now you have that, it's going to have in less. But for the students that I teach, persons, if you're coming for the first time, or whatever unit that is here, that is what you put as the denominator. So I go 1000 centimeter cube and 0.020 mole. Again, I'm experiencing some challenges with students understanding what this means. This is saying 19.93 times 0.020, and if you want to work it out on your calculator, you can work out that top part first and then you divide by 1000. Not sure why this is creating some problems. And of course, to make it even more beneficial, centimeter cube cancel centimeter cube, leaving our answer in mole. What did the question say? Using the calculate the average number of moles. So we see that we're getting to the answer. So what is the answer here?
Sir, 0.0003986.
much zeros? 3 zeros? 4 zeros?
4 zeros. 3986.
So 4-0.
Yes, sir.
So says everyone.
No, sir. Wait. Rub off the other one.
No
The
man,
last
3-0 me I get sir.
Alright.
Yeah. And then put 3986.
So we can't even round it off to 4. Not true.
Sir, I have a question.
Go ahead.
Is it 19.93 or 19.98?
Oh, 19.9. Sorry. I don't know where I get that 3 from. Thanks. Based on this. So based on this, guys, my apologies. So does that were we using, does this affect the calculation? Check for me, please.
Well, not when you round it off. It still get the 0004.
All right. And we get that. That's just a 1 mark. So yeah, worth it. Every mickle make a muckle. Yeah. The part E says from the equation, guys, from the equation. So automatically we need to revisit that equation. Determine the number of moles of iron ions, Fe2 plus, that reacted with 1 mole of dichromate ions. And I think we were discussing that even earlier. So right away, people can shout out the answer. So what was the equation here? We said that we have 1 mole, yeah? Yeah?
Yes.
So what is the mole ratio in terms of the dichromate and the iron 2?
1-6.
Beautiful. Everybody seen that? Because remember we did say, see it here, so the iron 2 here, and we said that the coefficient tells us the amount of moles. When we don't see a number, we know that there's a 1 there. So 1-6. So it took 1 mole of potassium dichromate to react with 6 moles of the iron 2 ions. Yeah? Let's go and get our 1 mark. And we are smiling at the exam. Are we not smiling at the exam? So 1 mole. Yeah? Whoa. So it says,
Sir, excuse me.
go again?
You can scroll back, please, so we can get the picture. Thank you.
So part F, what how long is your question long? How much, or even though we are do some whole heap of this cipher and all of that, how much is it? We almost gone an hour. So again, remember what them say? If you find yourself over 30 minutes, move on to the next question. But I've been doing some explanation and we're doing some talking and we're doing some reasoning because we're teaching as we go along. So that's why I kind of take up time. Yeah? But please remember, find out, them know, you know. The thing is, they know. So they make sure make that in a bowl and the knot is in all caps. Calculate the number of moles of iron in the iron salt sample. So watch me now. I know 1 mole. This is what I'm going to use. And the thing about titration, usually, it's like I always tell my students, as you go along, what you use, you're going to use it probably for the next question. So, see, if you look at the trend right here, so look at it. This table where we work out, all of that, it we use right here, so get this, and then we use this, get the number of moles, and then we use the equation to get the mole ratio, and so we are going to use this mole ratio to get the number of moles of iron. Here's how. So we know 1 mole of dichromate, and I'm just going to put the Cr2 is equal to 6 moles of what? Iron 2. Yeah? But which one of these? This again, I use this to create my conversion that I'm going to be using. So I know I had 0.0004 moles of dichromate. Not true. Going to be multiplying that. In other words, even if as a student, if you're a math person, you'll see it. Remember the ratio is 1 to 6. So every 1 mole of dichromate, you have 6 moles of iron 2, which is technically all you need to do is multiply whatever moles you got of the dichromate by 6. But just to show you, so I would have 1 mole of dichromate at the bottom and the 6 mole of Fe2 plus. So mole of dichromate cancel, mole of dichromate, leaving our answer in moles of iron 2, which we know is what? The 0.004 multiplied by the 6.
Point
0.0024.
I heard two response, so let me miss. Go again.
0.0024.
That's what we get.
yeah, man, I conquer.
And this is moles of iron 2. So again, follow-up question. It as we go along. Each part of the question is requiring you to utilize information from the periods. So them say calculate the mass of iron in the iron salt sample. So the mass of iron in the iron salt sample. So here's the thing. CXC come and give you this. And you done calculator, you know, use it. Then I give you for sure. So we know when I have 1 mole, it's supposed to weigh 55.8 gram. Not true? True?
Yeah, man.
So 1 mole, I get my conversion that I'm going to be working with, should weigh 55.8 gram. But I did not have 1 mole. I have 0.0024 moles. Will this be less than the 55 or
Yeah.
more than the 55?
Yes.
So less.
Yes.
Wonderful. Because if 1 mole away this, and this is nowhere near not even 1 mole. So again, once I do this, my conversion, people, my conversion. And I tell students, all my students, I say it to sound like a scratch record. I used to work with the cross multiplying, where 1 mole equal that, and so x gram are equal to that amount of mole. And it create havoc with me because students, sir, when me for divide, when me for multiply. And so I started using this method. So who goes to the bottom, who goes to the top?
Moles. 1 mole go below. And 55 point. Yeah. At top.
And so moles cancel mole. We were asked to calculate the mass. And this is why I like to do it like this because it, you know, so whatever our answer is going to be in is in grams. And they did ask us for mass. So what is this?
0.13392.
Let's use the entire thing. And that's grams. Yeah?
Yes, sir.
Wicked people, man. Not true. Calculate the percentage of iron in the iron salt sample. Because remember, I know, this mass that we have is just for the iron. Remember that there's probably more than likely something else because it's an iron salt. So as I said before, it would have been attached to whatever anion there was in the acid. So it could have been the chloride, could have been the sulfate, could have been the nitrate. So this iron is just contributing a portion to the mass. But if you look back, let's go back, way back. Initial part of the question, see it here? The iron salt sample, the entire thing was 0.500 gram. So all of it, meaning whatever else was with this salt, along with the iron, is present to give you that. So it's like I give you 10 questions and you get 5 correct. If I'm asking you your percentage in terms of mark, how much would you get? I give you 10 questions,
50%.
so you get 50%. What was the mental thing you did to get to that 50?
Work on the percentage, man.
Well, I wanted to hear. So it would have been the total questions you got correct
Yeah.
divided by the total questions.
The total amount of questions asked times 100.
Beautiful. So now, again, we figured out that the iron salt sample, the iron in it, have a mass. The whole entire sample has a mass. We want to find out what is the percentage the iron was contributing to that mass. Yeah? So we said calculate the percentage of iron in the iron salt. So we know, just like how we would have said, so the amount of mass that the iron is contributing, why my tree looks so? Mercy. Over or divided by physics teacher here. I say about over and cos. Divided by
There's 0.500.
times,
100 over 1.
and we know percentage we're working out. So what is that?
%26.78%.
You
Yeah?
sure?
Wait. So wait, what you got?
Oh, well, I might have to run it again. Might get 2.67 or 2.68. I'm run it again and see what I'm going.
So others can be working, you know. So just to double check.
Sir, I got
Oh, yeah,
26.84.
man. It's 26 there. I never put the point.
Okay, wonderful. What am I frightened with for people? Watch it again. Oh, how far the question? I, we're literally at I. So we went A, B, C, D, E, F, G, H, I. Why CXC so wicked, people? But anyway, never mind that. We're able to answer their question. We want to get all of the marks. Then say now the reaction between iron and dichromate is considered a reduction oxidation reaction, redox reaction. Define the term reduction in terms of electrons. And you smile, you know, because this soft, not true. Remember rig. And so we know reduction. Oh, nobody now completed.
Reduction is gain, man.
Gain of what?
Electrons.
Beautiful. And what if they ask you what is reduction in terms of oxidation number? What if they had asked you that?
That will be the loss of electron.
No.
Again, repeat.
What if they had asked you to define it in terms of oxidation number?
Oh,
Well, I think the oxidation number would be less.
Wonderful. So it would be decreasing. So reduction is a decrease in oxidation state or number. Yeah. So and this is a prime example I was talking to you about when I had the class. They will use these little things for you to gain a 1 mark. So again, this is what they do. I'm at J. J, I don't want to say the letters of the alphabet again. So all the way at J. In the reaction, Fe2 plus acts as a reducing agent, which we already knew, right? Define the term reducing agent. What's a reducing agent? And there's no one correct way to describe it. You can describe it in terms of what it does to the other substance in terms of electron as well. So the reducing agent will cause, I'm not sure if that's a hand or something.
It's when it causes an element in its free state to gain electrons.
So
Gain electrons.
beautiful. So we know the reducing agent is the agent that is causing the other compound or atom to gain electron. We could describe it in terms of what is happening to the reducing agent. What is happening to the reducing agent?
It's losing electrons.
Wonderful. So a reducing agent is also the agent that is being oxidized, hence losing electrons. So any one of those concepts you could use to describe what the reducing agent is. Because sometimes they're even specific. You see, just like how they ask you to do it in terms of electrons up there, they could have done it and say, yeah, define it in terms of electron. What is happening to the reducing agent? So that you would know that the reducing agent is actually losing electrons because it is being oxidized. So, yeah, mighty Father, we're gonna K. So, calculate the oxidation state. Now, I think we worked this out earlier. So, I'm not going to do another run through. I can go back to it. So that when we were looking at the question to determine the oxidation number, we worked it out. So let me jump back to it, do the explanation right here. This is where we did it. So we said that because the chromium is 2, instead of saying X to formulate our algebra expression, we would have said 2X. And we said oxygen has a -2 in terms of its oxidation number. When it is bonded in a peroxide, it would be -1. It's not in a peroxide now. Likewise, when you add or you sum the oxidation number of all the atoms in a polyatomic ion, it should equal to the charge of the ion. And so it should equal to -2. And so that's how we worked out, and we ended up with a +6. So for that question, they actually want you to show them how you would get the +6. So you don't want to just write down +6. So you calculate it. It says calculate, calculate. Very important right here. So if you just come and say +6, then of course you're not going to get the entire mark. You need to show how you got to this +6. Cool? Cool?
Yes, sir.
Then I'm at L. Mercy. How much mark this? Now ramp with question one, You see how much mark question one give you? Total of 25. 25 marks. How much would you have gotten out of this 25 if you gotten a similar question? Would you have been able to evaluate yourself as a student while I was explaining? Where did you find yourself not understanding? Was it when we started to calculate the oxidation number? Was it when we started to work out the moles? Because you have to, as a student now, identify your weakness. You see, I mean, for talk, but or explain certain things. If you want to know if a doctor, if you're looking at sick people or you're looking at persons, you have to know what a healthy person look like for knows that them sick. You have to know your weakness and you have to do things to correct that. So if you get this question and you realize say you did a buck on the moles part, you know you need to go and brush up on your moles. If you did a buck on the oxidation and reduction, knowing the definition and all of that, and you say, me no know what you mean by oxidation or me no know what you mean by reduction, then you need to brush up on that. Don't just sit there and say, you know what, me I go practice this question. Doing the question now will bring forth what you may be, you have to zero in on, right? So do your self-evaluation and be true to yourself. So if you know you never understand when me talk about the oxidation and reduction, you have to go over it. If you haven't done so in your classes, go over it so you understand. And then because there's other questions that will have that sort of concept in it. State one precaution that should be taken when carrying out the experiment. Anybody?
Make sure that the measurements are accurate.
So how may I go,
Where about this?
how may I go do that? Why not be more specific? How may I do that? You telling me that doesn't give me how. Because if me do it, if me are about to do this lab, and you enlighten me say, Mr. Thomas, so you have to be careful of make sure say your measurements are accurate. Does that really help me? How what am I supposed to do to ensure that?
You
So
have to read at eye level.
all right. So we are get little and you have to be careful too, because sometimes we talk about this word precaution versus source of error. We have to watch this word. And usually, what I said to students, maybe you should think about it in terms of safety. Precaution can include the whole concept of you getting the correct um, results. So, mentioning reading at eye level would have been worthy of a point. But also, one of the things that we did, or the persons who were carrying out the lab was using, was acid. You remember when they talk about phosphoric acid? Can go back to the question. Phosphoric acid is a strong acid, very strong, right? We were also using sulfuric acid, yeah? So the fact that you're using acid, that can be an area of concern. So your safety, we to tell the person while using the acid. And when it comes,
Wear gloves. Wear protective clothing and gloves.
wonderful, because you don't want the acid to basically, touch the skin, right? True.
Yeah, man.
So that finally, we keep people upper L, 25 marks. How did you feel about that?
One film I get 15 in here, sir.
All right, fair enough. Anybody
I
else?
think I'm not the whole 25.
Where you thought you would have not get the mark?
The the calculation for the oxidation number of the chromium.
Oh,
Yeah, for more of the oxidation reduction part of
aspect.
it.
So again,
Probably yeah.
you see where you need to, as I said, you can go back over that. Look back over the rules of calculating that. Anybody else?
I think I would have the same issue. I would get a 15 as well. The most part and the working out part, I think I would have an issue with that part.
So we need to go back over the moles and know how to apply, because you even did moles in this concept of moles in chemical equation was dominant right here. So once you do titration, moles in chemical equation will be very vital. Anyone else? All right, so we have two persons. We don't know what of them. Michael and Jennifer. So Michael and Jennifer were assigned a group project to investigate the effect of surface area. Surface area. Oh, I have to click this. Uh, so maybe we don't complete this question and we pick it up at the next session, but I'm going to work it out as far as possible because I have to do the explanation as well. A lot of things I'm going to bring out right here. So their investigation, again, this is a question one. Let me just say, see it here. Do not spend more than 30 minutes on question one. But them a give you one long bunch of questions. Not true. So if you reach 30 minutes, as I said before, there would have been a clock that the invigilator placed at the front of the room where you can relate and monitor your time. So if you pass 30 minutes, you probably move on to another question in the paper and then later you come back to it. So Michael and Jennifer were assigned a group project to investigate the effect of surface area on the rate of reaction. Now, rate of reaction is basically how products are created or the time in which reactants combine to form products. So how fast they do that. Now, the surface area, there are several things, there are several factors that affect rate of reaction. I know maybe this question will ask you some of those. And one of the factors is surface area. What is the relationship? Now, picture yourself. Today is Sunday, perfect day. I remember being tasked with cutting up the you call that the coconut for blend. Now, if you cut the coconut in larger slices, when you put it in the blender, would it be easy to blend out or harder?
Harder.
Easy.
Hard.
So it's harder because there is a concept saying that the smaller the items are, the larger the surface area. And so if you're a student who do biology, a matter of fact, even if you don't do biology, me know more while we're greedy and thing, and some people say them not chew rice. But how much time you supposed to chew your food before you swallow it? Now then there.
Until it palatable, man. Till it can go down easy.
How much time? What's the number of time prescribed to chew that food, that dumpling, that banana, that rice? How will buy a student name there? How much? A 32 time? How much time?
Boy, first my hear the concept, you know, sir. We can't answer that.
So one of the things why we chew our food so with that amount of refining the food, it helps our digestive system because the smaller the particles, the easier for the enzymes to break it down. Why am I mentioning all of that? Why am I talking about the coconut? Again, if you have a smaller particle, it will have a larger surface area, and so the faster the rate of reaction, right? You break up the things in smaller pieces so it can be easily dissolved. Some of the pills that the doctor prescribed, they will tell you to chew it. And that's one of the reasons. When you chew it, it will break up. And so you don't swallow it whole. It will be better to be absorbed in your bloodstream and carry out the task more effectively. Yeah? So surface area, there's a link. The smaller the particle, the larger the surface area. The larger the surface area, the faster the rate of reaction. So let's go again. The smaller the particle, the larger the surface area. And the larger the surface area, the faster the rate of reaction. All right. Now it says the reaction between zinc metal and dilute sulfuric acid. What type of reaction is this? What type of reaction is this? Anybody? So when I have zinc metal reacting with dilute sulfuric acid. Uno dede?
Yeah, man, me I go and listen.
Oh, so everybody quiet. So zinc metal, when you have a metal reacting with an acid, what the metal will do is to kick off the hydrogen and it will take its place to form the salt. You remember even a while ago, we were just focused on the iron salt, and I told you that the iron would be reacting with a particular acid, and it is what combines with the anion in the acid. So right here, the zinc would be combining with this. So that's how you get a zinc salt, which is zinc sulfate. So metal plus acid gives you a salt and hydrogen gas. Just excuse me 1 second, please. All right. So zinc metal would basically be reacting with the sulfuric acid. So as I said before, the metal will basically take the place of the hydrogen, and that's how we get the salt, and we would have end up with hydrogen gas. Not true. So Jennifer and Michael, they obtained 6 different grades of granulated zinc. 6 different grades, right? The grades represent the average size of the radius in microns. So when we look at it, if we talk about the grades, so diameter, how it go across, yeah? So you have 6 different sizes. Can draw one smaller than this. So 1, 2, 3, 4, 5, 6. So we're seeing the 6 different grades.
Yes, sir.
So even outside of this, guys, based on what I just said, which one of these grades would react much faster?
Top one.
So this one, meaning it will take less time for it to basically react with the sulfuric, sulfuric acid. Because we know the smaller the particle, the larger the surface area. The larger the surface area, the faster the rate of reaction. So as you switch these, we'll basically, and in this case, what you can be looking at is, a matter of fact, this did say it, and I should complete the question. So, but I just wanted to make this aware. So the 6 different granules. The grades represent the average size of the radius in micron of the granules. 6 experiments were carried out using different grades of zinc granules, which were reacted with an excess of 0.5 moles dm cube. Even this in itself, what that represent? Concentration. Not true? True?
Yeah.
So we know, if we wanted to, it's zero 0.5 moles in 1000 centimeter cube. Yeah? So the next thing is the temperature. So they have a set concentration and they have a set temperature. The same mass. So right here again, if you know you're doing an experiment and you want to ensure that things are set, what would you consider this being that all of them would have to be of the same mass? The mass would have been which one of the variable? Anybody?
The control variable.
Thank you so much. So we want to ensure, because again, if we use 10 in this case 0.55 gram, if we use 1 gram for one of the granules, 2 gram for the other one, 0.3 gram for the other one, that will influence our experiment. So we have to keep it constant. So even though the sizes are different, we have to ensure that we use the same mass. We have to ensure that we have them at the same temperature, because temperature is another factor that affects rate of reaction. Anybody knows how temperature affects rate of reaction?
Normally, the higher the temperature, the faster the rate of reaction.
Beautiful. And so if you had one of these, even though you have the small one at 0 degrees and you have the larger one at 100 degrees, in that case, it's no longer only about surface area. We have temperature as a factor that we have to consider. So if we want to see how surface area, in this experiment, Michael and Jennifer have to ensure that they keep these other factors constant. The next thing, the 0.5 moles dm cube of this dilute sulfuric acid. This is how concentrated the sulfuric acid is. So here's the thing. Concentration affects rate of reaction. So if I use another concentration, 1 mole, so if I use 1 mole dm cube, of course that is going to be more concentrated. Of course you're going to have more sulfuric acid, so the reaction must be faster. So they have to ensure that all of them were using the same concentration. We have to keep those constant, because the only thing that we should be changing is the surface area. And we're doing that by using different sizes. So now, what are they using to judge? And what we call that variable? What we call that variable? Talk to me now. We call it the responding variable. So we're looking for how fast or the time taken for the Michael and Jennifer to collect 100 centimeter cubes of the hydrogen gas in the 6 different scenarios. So again, which one of these you think you're gonna get the 100 centimeter cubes of hydrogen gas the fastest? Which one of these?
Top one.
The top one. Because we know it's going to be able, the zinc is going to be able to react with that sulfuric acid because the particles are much smaller. It's going to take a time because them one are too big and odious, and it's going to take a while. So while the sulfuric acid depend on the outside of this, you still going to have zinc on the inside when it break down yet, right? And so it's going to take a longer time. What was the manipulating variable? The manipulating variable is the concept of having the different grades of zinc granule. So I'm talking a little bit about, the experiment, because they probably could have asked you a question along that line. I'm not sure if they ask you anything like that. Yeah? So each time they do it, they react this granule, check how much time it takes to get 100 centimeter cube, they record it, right? So we get the whole concept of the lab. Everybody's supposed to understand what they're basically doing, right? Yeah? So help me out now. Experiment 1. How long did it take?
11 minutes.
How long did it take?
Oh, 11 seconds that.
Let's look back.
Seconds and minutes.
For the they didn't mention if it's seconds, Let me look at the more than likely seconds. Yeah. So 11 seconds. Because that's what we use as the unit in the table.
That is 40 seconds.
Please write these down so that we can use it in the table. How much this? Now, let me go ahead.
Look like 32.
I was saying, let me pause to explain. So again, you bring your ruler to the experiment. You'd have put your ruler on this line like this. Oh gosh, this is not drawing so properly. I want you to get the concept. So you lay your ruler down on the paper because sometimes your eye can deceive you, right? So you lay your ruler to really highlight where the point would have been. So that'll be right there. So for each of them, and so to avoid making a mistake, you do it like that. All right. So ensure you walk with it. I don't know if students are walk with them tools anymore when we are going to exam. Ruler, calculator. Also, we have to ensure that we get these items and get used to them, especially our calculators. So this one,
And 43. None.
so 1, 2, 3. But it look a little bit further than the 3. Looking at the center, not Joe?
That would be 43 point, would be 5.
this one?
That will be 52. 52.
This one?
I think that'll be 58. I'm not gonna up this yet.
No, I told me I use the song.
58.
So either 58.5, it looks like it's going in the center to me. But because it's complicated to maneuver this thing. And again, they won't kill you in terms of that, right? I'm gonna slaughter you. So the experiment right here, they did do one for you. So even if you never have any clue, probably you could have did it and figure out how them get to it. Not true? Because one is done for you. So we get the 11. What was the others? What were the others?
20, 32, 43.5, 52, 52, and 58.5.
All right. So let me, this one no word so much marks as the previous one. So it says, from the stopwatches displayed in figure 1, and it's very important. And matter of fact, see that them even tell you. So CXC are going good for you, man. On page 5, record the times for the hydrogen gas to be collected in column 3 in table 1. The time taken for experiment 1 has already been recorded for you. Yeah. But a 6 marks again, using your formula, rate equal 1 over time. Calculate the rate of the reaction for each experiment and record these values to 3 decimal places. Very important. They're giving you specifics. Work with it. In column 4, the rate of the reaction for the experiment has already been done for you. So, using the grid on page 7, plot a graph of rate. So, once we see rate versus time, the first variable goes on your y-axis, and the second one goes on your x-axis, if you never know. CXC has been making it very easy. Usually when them give these things, they might give you one blank graph. Now they're actually writing the figures, giving you the scale and everything, making it easier for students. Even giving you the formula. By right, you're supposed to know this. Because when anybody do the thiosulfate lab as yet? Thiosulfate lab?
Yes,
So,
sir.
Yeah, man, where you react and see how long the X takes to disappear. Yeah, that's a popular lab, a rate lab that we do. So again, you would have done in that lab the 1 over T calculation. So you should know. All of that, we see 6 and 5, 11 marks. So with the graph, we need to come back and work out the rate. So we know, and remember the 3 decimal places. We know they must have divided. So 1 divided by 11, that's how they would have gotten this number. Check it and see if that's what you get, please. 1 divided by 11.
Yes, sir.
All right, so quickly do 20. 1 divided by 20.
0.05.
0.05.
5.
And would I say 0? Because there's a 3 decimal place.
All right.
32.
0.031.
43.5.
0.023.
And again, I maybe just taking Sir values. Ensure that you
Mm-hmm.
double check for me, because we
Mm-hmm.
can make mistake. 52.
0.019.
58.5.
0.017.
All right. So would have been able to do that again, guys. If you notice, in terms of working with time, for me, what I tell students, even though this information is on the next page, because the graph is on the next page. See the graph here that you're supposed to plot. So what I say, instead of because maybe the booklet you'd have to be skipping back, please, you can just record these time for me so I can write them right at the graph. So I don't have to be going back and forth. Because you know you have to go skip back and skip back every minute. That takes up some amount of your time. So to be efficient, like how the table is on a different page, this information that you're going to plot, you basically just write it on the next side. Or write it beside the graph. Them can't penalize you for that. So we have this information. Just have this information for me because I'm going to ask for it, the rate. Everybody following so far? All right. So let's see if we can plot it quick and fast. So we have the time. The first time is 11 seconds. Not true. First of all, we need to work out. So on the x-axis, after I try, let me see if we can bring this up a little bit. Bring it up. I don't know if this is going to create no problem, but seeing the lines a little bit more clearer. So here, again, for persons who have been doing, this represents what? What that represent?
Fine.
It represents 1 centimeter. Yeah? We are trying to work out the scale of them use. Yeah? Work with me now. So,
Yeah, but that's a second below, you know, sir. A second thing that, you know, I know, length.
no, when you're doing the graph, remember you have to have a scale. So you're going to be saying 2 centimeters is equal, or it's 2. So every 2 centimeter is 10 seconds.
Okay.
So that's on your x-axis. Every 2 centimeters, because see the next one there. And this is something that students, as I said before, they don't usually do this. You would have to come and make your own scale. But again, it's not physics, so they're not going to pressure you too much. Maybe if it was a physics paper, you'd have to do that yourself, because that's one of the major things to, quiz you on the graph. The next one, on this axis, same 2 centimeters. So every 2 centimeters it go to 0.010, and that would have been what, in seconds? Meters per second, or 1 over t, second square. Well, not second square, but per second. So now we know that each of these then, so right here, so what that represent?
1.
All right. So the first time was what? You remember? We had 11. Remind me.
Yes,
Yeah,
sir.
11. Then 20. 32. 43.5. 52. 58.5.
All right. So 11. It was 11. So we go to 11. What was the rate?
The rate? Well, I never get all of them. 0.050. And 0.031
20
for 20. Yeah.
Sir, for 11, it was 0.091.
Thanks.
Oh, yeah, sir.
32.
32 was 0.031, 20 was 0.050, 43 0.023,
Hold on.
um,
Hold on. How shall I move so fast? 32 was 0 point.
32 was 0.31,
Mm-hmm. So wait. Oh, 32 and 20.
20, no,
Yeah,
20
change the
was
20. Change the 20, sir.
0.50.
Oh, all right. This look like a 8. Oh, gosh. All right. You know what? We capitalize. Some persons have them. But what I would have done, as I said before, all you need to do is just write them back here so you work them quickly. So we know we're at 11 and we're going to 0 point. Remember we spot 11, the people. We're going to 0.091, not true?
Yes, sir.
So with the right answer then. Yeah? The next one at 20. 20 and we go to 0.050. 0. Not true? 20, 10, so 20. So right answer. Yeah? 32. 32 is 0.31. So
Yes,
it's
sir.
30, 32. Hopefully, what you can do, you can get the paper printed and do the practice. And remember, we do have the past paper booklet, 3005 for it. So you can always link up and we get that to you. The
But I'm not seeing this one in the booklet.
one in there, this is
Nope.
the January, maybe
I
this is
was
it,
looking for it from the class start.
maybe not. I'm gonna look back on the cover, maybe not. So, but what you can do then is just print it because I sent it in the group. You can just get an opportunity to just print it. If I come into contact with you, because I know some persons are out of my, I can actually print it for you and give it. We are now at what? 43.5 goes to what again?
0.023.
43.23. Somewhere right here. Line. What's the next one? 52.
That is 0.019. And so it's not the group vicinity, they said they not the status, and the status to put them.
Yeah, man, I sent it in the group. You send it in that group?
No, it's on your status there.
Somebody in that group?
Yeah, I'm on the group. I'm in the group right now. Oh, yeah.
Oh.
Sorry,
So nobody need to say yeah, it in the group.
sorry, yeah, they are in the group.
You know, me not go crazy.
Yeah, I mean the
This
ones
same
from earlier.
this same questions. I sent it I think last night.
Last night you
Yeah,
said,
man. Yeah, man. Let me say long time, man.
Because I know I put it on my status, but I think I sent it in the group as well. But anyway, it's there. And I said if you can link me up and me get a printed for you. But the last one, 58.
0.017.
17. So 17 about here. Alright, so let me see. I go reduce this. Bring it down, bring it down, bring it down, bring it down, bring it down. So we can get a visual to it. You see there? Not true. Again, may I use my thing so it might not see if we can get it as best as possible. This thing is complicated. Sure. But we get the concept. Yeah? So which one of them here you think represent the one with the smaller diameter or radius? Which one of these represent the smaller radius? So 1, 2, 3, 4, 5, 6. Which one of them have the smallest radius?
The top one,
The
man.
first one.
Definitely, because the first one, the smaller the the smaller the size of the particle, the larger the surface area, which means it will create that reaction faster. So Jennifer, and let me explain in terms of Jennifer and Michael. I don't know what the two of them, but the two of them, they were able to get that 100 centimeter cubes of the hydrogen gas within 11 seconds, which means fast, don't it?
Yeah, man.
But as the size of the particles start to increase to the last one, which is the largest radius or radii, we would have seen where it took them 58.5 seconds because, again, the particles were just too large and that slows down the rate of reaction. Not true?
Mm-hmm.
So tell me now, as what was happening to the surface area right here? What was being done? Was the surface area increasing?
No, it reduced.
So we're decreasing the surface area,
Mm-hmm.
decreasing
Yeah,
the. So how did that affect the rate of reaction?
it take a longer time.
So it slows down the rate of reaction. So that's one of the relationship you want to see. Because remember, the whole point of the experiment to see how surface area affects it. So surface area, as you decrease the surface area, the rate of reaction will go, decrease. Not true. So as the larger, as the surface area becomes, smaller, right? The rate of reaction will go decrease. Yeah? So we got that from the experiment. It says, based on the graph, Tan deduce how the rate of reaction varied with time. How did the rate of reaction varied with time? How did it vary with time?
So it decreased.
No, you can't just say decrease. You're going to have to be more specific. So the rate of reaction, you're not saying the incorrect thing, but me just don't, you look on the line them. So where you would write, you just write the word decrease on the line.
So as more time passed, the rate of reaction decreased.
All right. Or as the reaction proceeds a longer time. Not true. Explain how the trend in the rate of reaction stated relates to the surface area of the zinc granules.
Sir, can you zoom in a little bit more, please?
Oh,
So,
sorry, let me bring it back up. Explain how the trend in the rate of reaction stated in B relates to the surface area. So what did we say? As the surface area decreases, the rate of reaction also decreases because as we've gotten bigger particles, so the bigger the particles, smaller the surface area, right? So as the surface area decrease, the rate of reaction also decrease. List 3 factors other than surface area that affect the rate of reaction. I know it's after 10, I'm just trying to complete. 3 factors other than surface area. What did we say?
temperature.
So temperature, concentration, light, what else?
Pressure.
Pressure, anything else? There's one more that begins with a C.
Catalyst.
Catalyst. And we know catalyst, it reduces the activation energy and all of that. So those are some of and again, students, please read the question other than. So every time, sometimes we get these questions, persons are come back and add surface area. You're not going to get a mark. Yeah? State one safety precaution that Michael and Jennifer may have taken during this experiment. Safety precaution. Spoke about this. Michael and Jennifer is also utilizing an Talk to me, people. They were also using sulfuric acid. I remember we just spoke about precaution a while ago with the lab previously. So we know that they should basically have, I know once it touch after 10, people, yeah. So they should also have on safety or protective gear, such as a glove, because they're handling the acid. Proper eyewear, yeah. So that's one of the major safety precaution right there. So just one way in which Michael and Jennifer may have controlled the temperature during the experiment. Now, we know, you see, water has a property. It doesn't respond, it doesn't change its temperature same time as the outside environment. So most of the time, what we do is to place the contents in a water bath. Because even if the temperature around changes, it doesn't directly affect the contents of your experiment right away, because it takes a while for the temperature of water to adjust. So usually when we're talking about controlling temperature, what persons do is to use a water bath. Cool?
Okay.
Oh, soon finish. Write a balanced chemical equation including state symbols for the reaction between zinc metal and sulfuric acid. Zinc, metal, all metals are solid at room temperature, plus sulfuric acid, all acids are, I'm not hear nobody shout it out.
Aqueous.
Thank you. We did say that the zinc is going to kick off the hydrogen, forming zinc sulfate. And we get hydrogen gas. Is this balanced?
Yes, sir.
And so, other going at the exam and feel say you're bright, so you need to you start putting some two and putting some. Sometimes the equation is balanced. You get a mark for the balance and you get a mark for the state symbols. You have to put in the correct state symbols. In order for you to work with the state symbols, you need to remember the solubility rules. Yeah? So finally, look what they did. Then bring in moles. Then go RTP. They want to calculate the total volume of hydrogen gas would be produced at RTP from 0.55 grams of zinc granules. So watch me now. We know what is the approach we're going to be taking, and then give you some information. See there? You know, even if you don't have a member. See there? So we know we are going to use this. If we can determine any mole of any compound, we can use it to find the mole of another compound, use mole ratio. So what is the step we're going to do? We want to find the mole of zinc. You'll use mole ratio to find the mole of hydrogen gas. Yeah? When we find the mole of hydrogen gas, we convert mole to volume of gas, and we would have been done. So let's go. How do we convert mole of zinc when we get mass of zinc? What is it that we have? 1 mole is equal to the atomic mass. Because we're dealing with an element. So not formula mass, because we're not dealing with an ionic compound. Not molecular mass, because we're not dealing with a molecular compound. Atomic mass, because zinc right here. And that's why they give you the relative atomic mass of zinc. So we know that when I have 1 mole of the zinc, it should weigh 65.4 grams. But I don't have 65.4. I have
0.55 grams.
thank you, multiplied, as I said before, I use this as my conversion, where I'm going to be creating a fraction from that. What determines my fraction in terms of denominator is what unit is there. If you feel comfortable using the cross multiplying, not a problem. So this will give me my answer in moles. What's my answer in moles?
0.08.
0.08.
Zero, zeros, 20.
0.008.
Yeah.
Right? Moles. And once I get to that, what was the next thing? So I find the moles of zinc. What next I said I would do? Use that mole of zinc to determine, or use mole ratio to determine. So let's go. The two things in question are the hydrogen and the zinc. I now know that I have 0.008 moles of the zinc based on the mass that I had. But I can now use mole ratio because I am not seeing a figure here. So I know there's a 1. I'm not seeing a figure here. And that's why it's important to balance the chemical equation before you can apply the mole ratio. So it's a 1-to-1 ratio. We're seeing that. And so if it is a 1-to-1, if I have 0.008 moles of zinc, then I also have 0.008 moles of hydrogen gas. And so what's the next step? We need to now convert this mole of hydrogen gas to volume. What's the relationship? They would have given us the concept of the condition, which is RTP. And we know 1 mole of any gas at RTP occupies 24,000 centimeter cube. But I did not have 1 mole. I have 0.008 moles. So again, if you notice, once I get to my conversion, school is over for me because I know exactly what I'm going to be doing. So I write down what I was given, and basically this is what I'm coming down from that calculation. So each time my given is changed, so it's now 0.08 moles. And I'm formulating a fraction. All right. So what is my volume? Where them there?
201.83.
Go again.
201.83.
And so, again, the first question, 25 marks. How much out of it? They did tie in moles at the end. You see that? So while we were looking at rate of reaction, And the last, then give you a 3 marks question, which requires your knowledge of moles. So as I was saying, sorry, you have a situation where you just get a question on moles alone. This question involves rate of reaction. It involves your knowledge about acids and base. You were able to balance the chemical equation. You were able to use moles in reaction. You also use moles with gas. So is that a hand? Not hearing. You're breaking up. I'm not sure if it's me alone, but I'm not hearing you. Look like I'm my internet. Cause
No, I'm not hearing them either, sir.
oh, not yeah.
No, it's 0.2.
Go again.
Yeah, I was saying that I was a bit confused with the calculation.
What happened? Something was wrong.
No, just like how you work it out because when I put it in my calculator, that's not the answer I got.
So that's
I
why
get
I'm asking.
192.
Yes, that's what I got.
So you're supposed to
Oh,
Yeah, 192 meters right now too. Sorry
where
about
where?
right at the end.
Yeah.
yeah,
So
instead of the 201.
Instead of 201 is 192.
so as I said before, guys, I take your answer as gospel. So again,
Oh, I'm sorry about that. I put in a wrong digit.
so 192
Yeah.
centimeter. All right, not a problem. So that's why I asked everybody to work so that we can highlight. So if you see it, you can just point it out because I'm not calculating it, like, which is sometimes bad, but I want to work with what you're giving me. All right. So everybody, we can make mistake, and this proves that again we need to double check our answers. Yeah. So outside of that, everything else would have been good. So again, I was just saying, when you evaluate yourself now, we saw acids and base come up in this question. We saw rate of reaction come up in this question. We saw moles in chemical equation. We saw balancing. We saw writing chemical um, state symbols for things. Would you have known that the acid is aqueous? Because those are the things that give you the little 1 mark. Would you have known how to calculate the moles of the volume of gas in terms of RTP? Those are things that you can evaluate based on this question. All right. So hope this session was beneficial. We look at 2 question 1s of different past paper, 2019 January, 2019 May, June. Remember to like, remember to share, and leave a comment. This is Mr. Thomas. Buckle down, tutor in service.